Hello everyone. Today we're going to have a tutorial to learn more about membrane reactors. Okay, so let's solve example 4.8, membrane reactor. According to the US Department of Energy, DOE, an energy saving of 10 trillion BTU per year could result from the use of catalytic membrane reactors as replacements for conventional reactors for dehydrogenation reactions such as the dehydrogenation of ethyl benzene to styrene and of butane to butene. The dehydrogenation of propane is another reaction that has proven successful with the membrane reactor. So we have here propane and it's getting dehydrogenated to propene. All the preceding dehydrogenation reactions above can be represented symbolically as A reversibly converted to B plus C and could take place on the catalyst side of an inert membrane reactor or inside a catalytic membrane reactor. Consider the following dehydrogenation reaction. A goes to B plus C reversibly, which is to be carried out isothermally in a catalytic membrane reactor. So that means we will not have any pressure drop. The equilibrium constant for this reaction is quite small at 227 degrees C. So the value of Kc is only 0.05 mole per liter, a very small value. The membrane is permeable to B, which is hydrogen, but not to A and C. Pure gaseous A enters the reactor at 8.2 atmosphere and 227 degrees C at a rate of 10 mole per minute. So we have the feed is A in the gas state, in the gas phase, and the conditions are given as well. Okay, so if you see here, the value of Kc is very low, which means the equilibrium is shifted more towards the reactant, right? In other words, you will not get the equilibrium conversion is not very high. طيب, so what? So we have to use a membrane reactor where B is diffused out of the membrane, which is the hydrogen. Consider the rate of diffusion of B out of the reactor per unit volume of reactor, that is R capital B, to be proportional to the concentration of B, i.e. RB equals Kc, all small letter, the K small letter, the C is small letter, times Cb, where Kc represents the overall mass transfer coefficient. The reactor volume is 400 liters. The specific reaction rate constant K and the transport coefficient Kc are given as follows. K equals 0.7 per minute and Kc equals 0.2 per minute. So basically this K represents how fast the reaction take place, right? While this K, which is related to mass transfer, represents how fast the B can diffuse through the membrane from the bulk inside the membrane to the bulk in the sweeping gas. So that's cover all the three resistances. A. Perform differential mole balances on A, B, and C to arrive at a set of coupled differential equations to solve. So basically, in order to solve this problem, we will need to solve the design equations. And you know, since it's a membrane reactor, X cannot be used to find the molar flow rate profiles. And this is something we explained earlier, because we said in a membrane reactor, the molar flow rates are not changing only because of conversion. They are also changing because of diffusion, right? So the conventional definition of X would be wrong to use to solve this problem. Therefore, we use molar flow rate since we have a gas phase reaction, and which means we have to derive and use 3 mole balances written in terms of molar flow rate, because we have 3 species. Okay, so I'm gonna skip the step because we have already derived the differential mole balance for the diffusing component, which is B in this case, and the non-diffusing component, which are A and C. Okay, then we have to plot the molar flow rates of each species as a function of the reactor volume. So we have to plot FA, FB, FC versus V. And then we have to calculate the conversion at the exit of the reactor. So let's do that. طيب, so let's do this together. The first thing is that we should write the design equation, correct? So let's write the design equation. Let's do the balance on A. So we have dFA over dV equals RA, correct? Okay, what about the initial conditions? Well, we know that at V equals to 0, FA equals FA naught, and it equals, well, I don't remember the value now. However, it has a value. Okay, let's do that. And of course, we're going to use this equation we're going to use this in polymath. Okay, let's look at the other differential equations. So what do we have? Okay, then we write the mole balance for, I believe, hydrogen, right? Okay, so let's do that. dFB over dV equals, and because hydrogen is diffusing out, the equation which we derived was RB minus R capital B. Okay, and here we also introduce the initial condition, provide the initial condition at V equals to 0, if B equals 0. Okay, here if A naught was 10 mole per minute, of course, 10 mole per minute. Okay, let's go to C. Let's write the differential equation for C, the design equation for C. dFC over dV equals RC, because C here is not diffusing out or in of the membrane. So it's the conventional plug flow reactor design equation. Of course, all these design equations are for the same reactor. We don't have 3 different reactors, it's one reactor. Okay, and at V equals to 0, we know that FC equals to 0. Okay, so we're gonna plug in all these equations into the software. Therefore we're gonna frame it so we'll know which equations to plug, right? Okay, so we have all these guys. Come on. all of these will be plugged into the software. Okay, remember Shabab the concept of the logic between these steps? It was based on the fact that we need to solve the design equation. However, when we write the design equation, we introduce a variable. In this case, it's the rate fraction, so we provide an equation for it, and so on. Okay, and here in this case, we are providing a variable which is RB, the R capital B. So we need to provide an equation for this, and luckily we have a very simple equation which states that maybe we should write it in black. Okay, RB equals KC times CB. Okay, and we're gonna need this equation as well to plug it in. Alternatively, we can write this equation at the end. Okay, so let's continue. Right, so we are done with step number 1. Now let's go to step number 2, which is simply writing the rate law. It's an elementary reaction, so the rate law is simply written as minus RA equals KA times CA minus CB times CC divided by KC. So that's the rate law. I don't like the way the C was written. Yeah, maybe this looks nicer. Okay, so now we have a rate law. Looks very nice, right? Okay, so did we introduce any variable here? Well, we have the concentrations here. They are variable. We're going to take care of them at the following steps. Ka and Kc are constant, so no big deal. Type. Let's go to the third step, which is to utilize the stoichiometry. Let's utilize the stoichiometry. Okay, here we said, Shabab, see we have RA, we have RB, and we have RC. However, we only provide an equation for RA, therefore we need to relate these rates together. So let's relate these rates together. So this is the first step. Okay, so how do we write it? That's very simple. We know that RA divided by minus 1 equals RB divided by plus 1 equals RC divided by plus 1. Correct? And all of this from the stoichiometric numbers. So therefore RB equals minus RA, and RC equals also minus RA. Okay, and we need to, of course, frame them as well. Okay, so let's go ahead and frame them. Oh, we need this as well, so we're going to frame it as well, or we can leave the framing to the end. Okay, right, so that's one step. Let's look what we can do in the stoichiometry. In the stoichiometry, we also have to relate concentration, which appear in the rate law. So, this concentration which appear in the rate law, we need to relate them to the molar flow rate, which appear in the design equation. So let's do that. Okay, so I'm gonna write a general one, then we're gonna write for the three of them. Type. Let's start with CI. Oops, what did it go to? Red. Let's write it in black. So CI equals Fi over epsilon. Correct? Fi over epsilon. Okay, what does Fi equal? Well, Fi equals Fi, right? I'm not gonna change Fi, we're going to write in terms of x because x is not my preferred variable here. What does epsilon equal? Epsilon equals epsilon naught times the 3 correction factor. The first one is related to number of moles, Ft over Ft naught, right? Okay, what about the second correction factor? It is T over T naught, and then we have P naught over P. Can we simplify? Yeah, we can simplify. So this guy goes to 1 because we have isothermal operation. And P naught over P almost 1 because we have negligible pressure drop. Okay, very good. Okay, so let's simplify it further or rearrange it further. So Ci equals, I can put Ft naught with epsilon naught, and then you have Fi with Ft, which means I can write Ci as Ct naught times Fi over Ft. Okay, so this is a general equation that we can write it for A, B, and C. Right. So for Ca, it will be Ct naught times Fa over Ft. And for B, it will be Ct naught times Fb over Ft. For C, it will be Ct naught Fc over Ft. Okay, so we're gonna use these 3 equations, and I'm gonna frame it for you here. Okay, again the question is, did I introduce any variable? Yes, if t is a variable, so we need to provide an equation for, and we know that if t equals fa plus fb plus fc. Of course, all of these guys, 3 guys, are variable. Fa, fc, and fb, they are all variable. However, we do have an equation for, right? Remember the design equation? Okay, very good, very good. طيب, any other variables? Well, nothing for now. So let's continue. Now, of course, we are in step 4 and 5, which is to evaluate. Step 4 and 5, which is combine and evaluate. Well, first we need to evaluate the parameters, and then we need to evaluate the equations. So let's see, let's walk backward. Let's look at the equations for the Ft. There are no parameters we need to evaluate. Oops, we have Ct naught. Okay, we have Ct naught. So let's evaluate Ct naught. Okay, Ct naught equals, what is the concentration and the total concentration at the entrance equal? Well, you guys know that total concentration equals P naught, right, over RT naught. Of course, both P naught and P are constant. P naught and T naught are constant. Okay, so you don't need to write the naught if you don't want. Anyway, so let's continue. So we need to provide value for P naught, which I think it was 8.2 atmosphere, and then T naught, which equals what was it? It was 227 plus 273, correct? And this is 500 Kelvin, and then we need to provide equation for R, which is 0.082, and of course the units are atmosphere, liter per mole, Kelvin. Okay, what else? Of course you can write the exact number of R. Okay, what else? Okay, so we're done here with CT naught. Okay, let's go backward. I think the previous equations there, let's see what we had earlier. We had also RB, yeah, we had RB. Okay, so let's work with RB. So RB equal KC, right? So we have to write the value of KC. This is the one related to mass transport, so that's why it's small letter KC, and the value was 0.2. Okay, 0.2 per minute. 0.2. Oops, having trouble to write it per minute. And then we had also K, which was 0.7 per minute. And then we had the capital K, small c, which is the concentration equilibrium constant, which simply equaled 0.05 mole per liter. Okay, anything else we are forgetting? I don't recall that we are forgetting anything here. Okay, so we provided all the information. Okay, I believe also the question was asking for x, so let's write an equation for x as well. What does x equal? X equals FA naught minus FA divided by FA naught, correct? And the question is this definition correct or not? Well, let's look at FA. Does FA reduce because A is also diffusing out, or it just decreases because of conversion, because of reaction? Well, in this case, only B is diffusing out, so A is not diffusing out, therefore FA is reducing only because of conversion, so this equation is correct. Okay, so let's frame all of these parameters that we need to plug them in, right? And of course we need to provide one more thing, which are the value for the initial volume. So V initial, of course, is 0, and then V final was also given as 400 liter. So we'll need these as well. Okay, so let's go and plug in all these equations that we framed into Polymath and solve the problem. There we go. We got the result here. Right. Very good. So let's do some plotting to understand what's going on. Okay, so this is the solution for the catalytic membrane reactor. So as we see, the molar flow rate of FA is decreasing. That is because A is a reactant, and the molar flow rate of C is increasing because it's a product. So as the reaction progresses, as we go down the length of the reactor, If A decreases, if C increases. But we have something really interesting here. What's happening to Fc, the molar flow rate of the hydrogen? Well, first it's increasing, right? First it's increasing, and then it reaches a maximum value, then it decreases. Why do you think this is happening? Why do you think this is happening? Well, let's look at the design equation or the mole balance of B. Type, what was it? It was dFB over dV equals RB minus R capital B, correct? So how B is changing really depends on a competition between RB and this RB, right? So when I say dFB by dV, then we are talking about the slope, right? When you plot FB versus V, which we have it here, we're talking about the slope. So in the beginning, the slope is positive, right? The slope is positive here, right? So that means if B is increasing, why do you think it's increasing? So this value should be positive. That means this guy is greater than this guy. That means the rate of reaction, in other words, the rate at which B is forming is more than the rate at which B is diffusing out. Therefore, if B is increasing, why is that? Why RB is more than RB, R capital B? Well, because the concentration of A is large at the beginning, right? Therefore, the rate of formation of B is large, while the concentration of C is small, right? Tamam. Because the CB is small, therefore RB will remain small. That's why the rate of the production of B is more than the rate of production of diffusion of B. So let's plot it and look at it. Let's plot these two variables. Okay, so we are plotting here RB. So this is my RB, and which is the rate of formation of B, and the other line is the here, this is the R capital B. Okay, so at the beginning you can see that RB is much larger than the rate of formation of B is much larger than the rate of diffusion of B. Therefore, the FB is increasing. So this happens until it reaches a maximum value. And at this maximum value, actually we have both rates are equal. However, after this, we'll see that the rate of formation of B decreases, right? So RB, R capital B, the rate of diffusion almost remains constant, because the concentration of B almost remains constant, but the rate of formation of B decreases. That's because the concentration of A has decreased, and also of course the concentration of C has increased, and because it's a reversible reaction. Therefore, all of these, the decrease in concentration of A and the increase in concentration of C actually reduces the rate of reaction. Therefore, here we have the rate of reaction drops to a rate which is below than the rate of diffusion of B. So B is diffusion at a rate which is faster than the rate at which it is formed. Therefore, its molar flow rate will decrease, and we will get a conversion of 56.7%. طيب. Let's go to the last requirement. What would be the achieved conversion if the reaction was carried out in a conventional plug flow reactor? So if you are not running this reaction in a membrane reactor, you're just running in a conventional plug flow reactor, what would be the conversion? Well, do I need to solve it all together from the beginning? Or I can just simply do one step and I can solve it in less than a minute? Yes, so what the difference between the plug flow reactor and the membrane reactor is that plug flow reactor there's no diffusion. Therefore, Kc equals to 0. The overall mass transfer coefficient equals to 0, which takes Rb to 0. So let's do this change only, and then let's compare the conversions in both cases and explain the obtained result. Okay, so when you use plug flow reactor, the conversion is much less. Right? That one was above 50%, this is below 50%. Let's look at the molar flow rate. So if A decreases and then it levels off. If B and if C increases and then they level off. So what's happening? What do you think is happening, guys? Remember the reaction was A goes to B plus C irreversibly. So basically in a plug flow reactor, after maybe 1/4 of the reactor, the reaction reaches equilibrium. The reaction reaches equilibrium. Therefore, no more Fa converts to B and C, right? Actually, the rate at which A converts to B and C is the same as the rate at which B and C convert back to A, right? So the net rate of consumption of A is 0, the net rate of formation of B is 0. Let's look at the RB. Yes, see here, somewhere here. Okay. So that's around, let's say around 160 liter. So 160 liters around somewhere here. So here the rate of reaction almost drops to 0. Correct? Almost drops to 0 because equilibrium is reached. So the conversion here, despite the fact that I'm giving the reaction mixture more volume, right? All of this is a volume of the reactor, but actually the conversion is not going beyond 44.7%. That's because equilibrium has been reached already. In the contrary, when we use membrane reactor, the longer the reactor is, the more conversion you get, because as we increase the length of the reactor, you'll have more B is diffusing out, and the reaction is shifted more, the equilibrium is shifted more forward, right? And we know that the conversion here is limited thermodynamically. So actually why we don't get more than 50% conversion in a plug flow reactor, because the kinetic is very fast and equilibrium is reached very fast, and then I cannot go beyond the equilibrium conversion, right? So if I want to achieve conversion more than 44.7, right, I had to play with thermodynamics. How do I play with thermodynamics? One method would be to pull one of the product out of the reactor. Therefore, I can shift the equilibrium forward. Okay, now I want you to think about different methods of increasing the conversion beyond this value. Well, the first thing is to increase the volume, right? Because if I increase the volume, more B will diffuse out and more A will be converted to B and C. Okay, that's good. What else? Yeah, we can use a membrane with maybe larger pores to allow the rate of diffusion of B to be faster. Remember, RB equals Kc times Cb. So if the value of Kc is larger, therefore this will be larger, right? And then I can pull the reaction more forward because I'm pulling more B out of the reactor. Okay, what else? Well, what about the K capital C? Again, the reaction is limited thermodynamically, so maybe if I operate at higher temperature, sorry, because this reaction is endothermic, at higher temperature, where the value of Kc is higher, and luckily the value of K is higher and the value of Kc is also higher. Okay, so if I operate at higher temperature, the value of Kc will be higher, therefore the equilibrium will be shifted forward as well, and I'll be able to get more conversion. Okay, so I hope this problem was really useful to help you out to practice designing membrane reactors, and also I hope it also helped you to clarify between X and XE and give you some more insight into the difference between kinetic and thermodynamics. I think this was very clear because again the reaction here or the conversion here was limited thermodynamically, as the conversion did not go beyond 50% because thermodynamics was limiting the conversion because the equilibrium conversion was less than 50%. Therefore, we needed to, and in fact, we did not have problem with kinetics, right? Actually, the rate of reaction was very fast. In fact, I have reached the equilibrium in the first third of the reactor because the kinetic was very fast. Okay, but this fast kinetic did not really help me to get conversion beyond 50%. But I needed to solve the problem by tackling the problem related to thermodynamics. And in this case, as we said, we learned it by allowing one of the product to diffuse out, and therefore we were able to shift the equilibrium forward. And also we discussed other few things on how to increase the conversion through increasing Kc and this Kc. This will help, but not as much because I don't have problem with kinetic anyway. Correct, and also increasing the volume of the reactor. Okay, with this we reach the end of today's lecture, and we'll meet soon inshallah. Bye for now.